Hello, in today's video we shall be looking at Bernoulli's equation. Now, if a liquid is flowing in a pipe, that liquid possesses three forms of energy, and the first is potential energy. If a liquid of weight W is at a height of let's say Z above the datum level, the potential energy of that system is P equal to WZ. Know that Z is the height above the datum level. Now we can therefore say that the pressure, so we can say that the potential energy per unit weight, is equal to Z. So this potential energy per unit weight is measured in Newton meters per Newton and is measured as a length or as a head, and can be called the potential head. So this is called the potential head. Next is the pressure energy. When a fluid flows in a continuous stream under pressure, it can do work. So our pressure energy per unit weight is equal to the pressure over the specific weight. So this is pressure energy per unit weight is equal to pressure over energy. This is equivalent to head, so we call this the pressure head. This is called the pressure head. Now, if you remember from our previous class, we said that specific weight is equal to density times the gravity. So therefore we can say that pressure energy per unit weight is equal to the pressure over density times gravity. So this is the formula for pressure head. The next type of energy that a body possesses when it is flowing is called the kinetic energy. Now, the kinetic energy per unit weight, so our kinetic energy per unit weight is equal to V squared over 2G. This is our kinetic energy per unit weight. It is also measured as a length or a head, so we call this the velocity head. So this is known as the velocity head. Alright, so therefore we can say that the total energy of fluid flowing in a system is known as H. This H is equal to the potential head plus the pressure head plus the velocity head. All right, so we can write this in equation form as H is equal to the potential head, which is Z, plus the pressure head, which is P over specific weight, plus the velocity head, which is v squared over 2g. So this is the total energy of the fluid that is flowing in a pipe or in a system. So let's look at Bernoulli's equation. What is Bernoulli's equation? Bernoulli equation states that the total energy of each particle of a body of fluid is the same, provided that no energy enters or leaves the system at any point. So please, you must note that the division of this energy between potential, pressure, and kinetic energy may vary, but the total energy remains constant. In mathematical form, it states that H, which is the total energy, is equal to Z plus the pressure over specific weight plus V squared over 2G is equal to a constant. This is the principle of Bernoulli equation. Also, I want us to note that if a fluid enters a pipe from a point, let's say point 1, and leaves that system from point 2, we can also use Bernoulli's equation to analyze that fluid. So that means that we can say that the total energy at the point of entry is equal to the energy at the point of exit. Okay, so that means that our energy at point 1 becomes Z1 plus the pressure at the entrance over the specific weight of the substance plus the velocity at which the fluid enters over 2 times gravity is equal to Z2, which is the height above the datum level at section 2, plus the pressure at which the fluid leaves the system over the specific weight of the same fluid, plus the velocity at which the fluid leaves the system over 2 times g. And please note that our g is a constant, is equal to 9.81 meters per second square. And please also note that the specific weight of water is equal to 9.81 kilonewton per meters cube. And also the specific weight of mercury is equal to 132.9 kilonewton per meters cube. So these are the two common fluids that we shall be using as we analyze the flow of fluids. And please, I want us to also note that many phenomena regarding the flow of liquids and gases can be analyzed by simply using the principle of Bernoulli. Now, let's look at the limitations of Bernoulli equation. Bernoulli equation is the most important and useful equation in fluid mechanics. Now, Bernoulli equation has some restrictions in its applicability. It has some restrictions in its applicability, and they are: number one, the flow is steady. The flow is steady. as the first one. Number 2, the density is constant. Number 3, friction losses are negligible. Friction losses are negligible. And number 4, the equation relates to state at 2 points along a single line. The equation relates to the states at 2 points along a single line. Okay, so these are the or some restrictions in applying Bernoulli's equation. Let's look at the application of Bernoulli equation. Now we can apply Bernoulli equation to different systems or to different devices. So the first device is the horizontal pipe. So what you are seeing on your screen is an horizontal pipe, and this, from this point to this point, is our datum level, which is our Z. So this is 36 meters is our Z. So this point right here is our datum level. So it's the datum level. So here we are given a question. If water is flowing at a pressure of 490 kilonewton per meter squared, so our pressure is, I can write my given data. So our pressure is 490 kilonewton per meter squared. That can be written as 490 times 10 to the 3 Newton per meter squared. Okay, so what is the total energy per unit weight? So our total energy is not given to us, that is our unknown. If it is flowing with a velocity of 3.9 meters per second, so our velocity is given to us as 3.9 meters per second above the sea level as shown in the diagram. Remember that our height above the datum level is given as 36 meters. So for us to find the total energy per unit weight, we have to use the formula for datum, which says that the total energy is equal to Z plus a P of pressure over the specific weight plus V squared over 2G. Now please remember that the fluid flowing in this pipe is water. So our specific weight for water, the specific weight for water is 9.81 kilonewton per meter squared. We can per meter cube. We can convert these to Newton per meter cube. That gives us 9.81 times 10 to the 3. So that gives us 9,810 Newton per meters cube. So that is the specific weight of water. So therefore we can put in the values into our equation. So therefore we have our height above the datum level is 36. So we have 36 plus the pressure of the fluid is 490 is 490 times 10 to the 3 over the weight of water is 9810 plus the velocity of the fluid is 3.9, so all squared open brackets is 3.9 all squared over 2 times gravity is 9.81. So therefore our energy becomes 36 plus 490 times 10 to the 3 divided by 9810 will give us 49.95 plus 3.9 squared divided by 2 times 9.81 will give us 0.78. So therefore our energy per unit weight is 36 plus 49.95 plus 0.778, that gives us 86.73 joules per newton. So here is our total energy per unit weight. Here is another application of Bernoulli equation using an inclined pipe, or we call it a bent pipe. Now here we have the pipe which is inclined or bent. At section M we have a datum level which is let's call it our ZM. Then at section N we have a different datum level, let's call it ZN. Okay, now please don't forget that this point here is our datum level. So the fluid is flowing from section M to section N. Now here's a question. It reads, an inclined pipe MN as shown measures 5 meters and 3 meters respectively above the datum line. If the diameter at M and N are both 10 meters and 3 meters, so the diameters, so let me call this, the diameters at M is 10 meters. It is very important to always label your work. And the diameters at N is 3 meters. Very important to show this on diagram. Now the water pressure and the velocity at M is 250 Newton per meter squared and 0.5 meter per second respectively. So the pressure at M is giving us 250 Newton per meter squared, and the velocity at M is giving us 0.5 meters per second. We're asked to calculate the pressure at N. So the pressure at N is not given to us. Remember, if you look at this diagram, you will see that we are not given the velocity at N. So that means that before I can find the pressure at N, I have to find the velocity at N. So for me to find the velocity at N, I have to use the principle of continuity equation. So therefore I can say that to find the velocity at N, we use the principle of continuity. I hope everyone remembers that principle. which states that the discharge flow rates at section N must be equal to the discharge flow rates at section N. Alright, so therefore remember that the discharge flow rate is the area at section M times the velocity at section M is equal to the area at section N times the velocity at section N. Okay, now please note that the area of the section will be given as pi d squared over 4. So the area at M is pi dm squared over 4 times Vm is equal to the area at N is pi dn squared over 4 times Vn. Alright, so what next? If you look at this equation carefully, you see that the pi over 4 will cancel the pi over 4 on both sides. So we are left with the diameter at M squared times Vm is equal to the diameter at N squared times Vn. So what next? To get the velocity at N, we can divide both sides by diameter at N squared on both sides. So I'll divide this side by the diameter at N squared, divide by the diameter at N squared. So these cancel out this. Alright, so I'm left with the velocity at N is equal to diameter at M squared. Diameter at M is given as 10. So we have 10 squared times velocity at M is 0.5. So we have times 0.5 divide by diameter at N, which is 3, so it's 3 squared. So guys, if you put this in your calculator, the velocity at N should give us 5.6 meters per second. So that is our velocity at N. So it is 5.6 meters per second. So now I have found the velocity at N, so I can easily find now the pressure at N. So to get the pressure at N, we have to use the Bernoulli's equation. So therefore, to get the pressure at N, we use the Bernoulli equation. So remember that equation was given us Z1 plus the pressure 1 over the specific weight of the water plus V squared over 2G. Now this time I'll call this my N. All right, this is the N. This is my velocity at N. Okay, is equal to the height at N plus the pressure at N over the weight of water plus the velocity at N squared over 2G. So we're asked to find the pressure at N. So we have to transpose. When we transpose, we move this Zn to my left. It becomes open bracket. It becomes Zm minus Zn. All right, plus Pm over W plus the pressure at M over the specific weight plus Vm squared minus Vn squared over 2G is equal to the pressure at N over the specific weight. Now, for me to make my pressure at N a subject, I have to divide, or I have to multiply both sides by the specific weights. So that means to get my pressure at N, I multiply the left side and the right side by the specific weights. So I'll multiply this side by specific weights, and I'll multiply everything right here by the specific weights. That means that these cancel out this, so I am left with the pressure at N is equal to the specific weights, which is of water, times the datum level at M minus the datum level at N plus the pressure at M over the specific weights of the fluid plus velocity at M squared minus velocity at N squared over 2G. Alright, so what next? We put in our values. So therefore my pressure at N is equal to, now the specific weight of the fluid here is water. So remember that the specific weight of water is 9810 from bracket. My Zn is 5 and Zn is 3. So 5 minus 3, we have 5 minus 3 plus the pressure at Pn is given as 250. Okay, it's 250 divided by the weight of water, which is 9810 plus velocity at N is given as 10, that's 10 squared, minus velocity at N is given as 5.3, sorry, 5.6, yes, 5.6, given as 5.6, remember, or squared, divide by 2 times G, which is 9.81, bracket close. So what next? Oh, sorry, the velocity at M should be 0.5. So this should be 0.5. It's not 10. So this is the velocity at N is 0.5 or squared. All right. So therefore we can log in our values. So I have my 9810 open the bracket, 5 minus 3 is 2 plus 250 divided by 9810 is 0.0255, 0.0255 plus 0.5 squared minus 5.6 squared divided by 2 times 9.81, will give us negative 1.5856, 1.5856, bracket close. So therefore we have 9810 open brackets 2 plus 2 plus 0.0255 plus minus, remember that plus minus becomes a minus, okay? So 2 plus 0.0255 minus 1.5856, that gives us 0.4399 as 4399. So therefore our pressure at N is 9810 times 0.4399, that gives us 4315.4 Newton per meters squared. So this is our final answer for the pressure at N. Here is another question. We are told that mercury is flowing along a pipe with a velocity of 10.2 meters per second. Express this as a velocity head in meters of mercury. Determine the corresponding pressure in kilonewton per meters squared. So in this case now we're having mercury flowing in the fluid. So if you remember, the velocity head is h is equal to v squared over 2g. This is the velocity head of the mercury. So therefore we can put in the values. The velocity is given as 10.2, so we have 10.2 or squared over 2g, which is 2 times g. G is 9.81. So therefore 10.2 squared will give us 104.04, 104.04 divided by 2 times 9.8 will give us 19.62, 19.62. So therefore our velocity head h is equal to 104.04 divided by 19.62 will give us 5.30 meters. 5.30 meters. So this is the velocity head of the mercury. Now the next part of the question, we're asked to find the corresponding pressure. Now we also know that pressure, or we know that the corresponding head is also equal to pressure over the specific weight of the substance. In this case, the weight of the substance is, or the fluid in the system is mercury, so therefore is the weight of the mercury. And please note that weight of mercury is equal to 132.9 kilonewton per meters cube. I don't have to convert these to Newton per meters cube because the question we're asked to leave our answer in kilonewton per meter squared. So I can leave my weight of mercury in this form, so as to have my answer in kilonewton per meter squared. So therefore I can find my pressure by doing a transpose. So we have pressure is equal to the head times the specific weight of mercury. So therefore our head is 5.30, so 5.30 times the specific weight of mercury, which is 132, is 132.9. So therefore our final answer is the pressure is therefore 5.30 times 132.9 will give us 704.37. Give us 704.37 kilonewton per meters squared. So this is the pressure, or the corresponding pressure in kilonewton per meters squared.